The dawn of a new age, the Trinity test, and the birth of modern physics. What lies within the smallest building blocks of the universe? Can the tiniest particles hold the power to reshape history and redefine the very fabric of civilization? These questions, once the domain of philosophers and speculative thinkers, gained terrifying clarity in the pre-dawn hours of July 16, 1945, when science unlocked one of nature's most devastating secrets. In the barren expanse of a New Mexico desert, the first light of dawn struggled to rise above the horizon. 30 minutes before sunrise, the stars had already surrendered to a shadowless blue hue suffusing the desert floor. The stillness was deceptive. This unassuming patch of ground had been meticulously prepared for a singular moment in history. Rising alone at the base of the Oscura Mountains, a 30-meter steel tower bore an ominous payload at its apex. Surrounding it, at precise intervals 9 kilometers away, 3 partially buried shelters housed a mix of soldiers and scientists awaiting the culmination of years of groundbreaking yet harrowing research. The air crackled with anticipation as a voice on the public address system began the countdown. Lying prone on the ground with their feet pointed toward the distant tower, the observers could not see the device itself. But they would soon witness its unimaginable power. At precisely 5:30 a.m., the quiet was shattered by an earth-shaking explosion. The steel tower evaporated, the desert floor melted into green glass, and the dim light of dawn was instantly overwhelmed by a searing brilliance that turned night into day. This was the Trinity test, the first full-scale detonation of a nuclear bomb. It marked the dawn of a new era in human history, one that would shape geopolitics, scientific discovery, and humanity's perception of its place in the universe. The events leading to Trinity began decades earlier, in a time when the atom was merely a theoretical curiosity. For centuries, philosophers and early scientists had debated whether matter could be infinitely divided or if there existed fundamental, indivisible units. By the early 20th century, experiments had revealed that atoms were not the ultimate building blocks of matter. Instead, they contained even smaller constituents, nuclei surrounded by electrons. The discovery of the nucleus opened the door to a new understanding of energy and matter. In 1938, German chemists Otto Hahn and Fritz Strassmann, along with physicists Lise Meitner and Otto Frisch, discovered nuclear fission, the splitting of an atomic nucleus into smaller fragments, accompanied by a staggering release of energy. This revelation coincided with the outbreak of World War II, and the implications of harnessing such power were immediately apparent. Albert Einstein, along with physicist Leo Szilard, penned a letter to President Franklin D. Roosevelt, warning that Nazi Germany might develop a powerful new weapon based on nuclear fission. This letter spurred the United States to initiate the Manhattan Project, an unprecedented effort to harness atomic energy for military purposes. The device tested at Trinity, nicknamed the Gadget, was a plutonium-based implosion bomb. Its design relied on carefully shaped explosives to compress a subcritical plutonium core into a supercritical state, triggering a chain reaction. This reaction released energy equivalent to 21,000 tons of TNT within a fraction of a second. The result was both a triumph of human ingenuity and a chilling demonstration of the destructive potential of nuclear science. The explosion not only vaporized the steel tower but also left a crater at the site, its floor transformed into a sheet of green, glassy material later named trinitite. Above the desert, a massive fireball ballooned upward, forming the now iconic mushroom cloud, a grim symbol of the nuclear age. If not for the exigencies of World War II, nuclear science might have taken a slower and more measured path. Before the war, the exploration of the atom was a niche pursuit, limited to small advancements and incremental discoveries. The pressures of wartime, however, accelerated this research, transforming atomic science into a cornerstone of modern physics. The success of the Trinity test marked a turning point, not only in military history but also in humanity's understanding of the universe. The same principles that unleashed the bomb's power inspired a deeper inquiry into the nature of matter and energy. The atom was no longer just a fundamental particle, it was a gateway to a hidden world of fields, forces, and particles, where the rules of classical physics gave way to the strange and counterintuitive laws of quantum mechanics. As the glow of Trinity faded, it left behind more than a mark on the desert floor. It ignited a scientific revolution. What are the true building blocks of the universe? How does energy shape matter at its most fundamental level? These questions propelled scientists deeper into the quantum realm and further back in time, seeking to unravel the mysteries of creation itself. The discovery of nuclear fission was just the beginning. The journey to understand matter led to the exploration of subatomic particles, the development of quantum field theory, and the realization that our universe operates on a tapestry woven from particles and waves, probabilities and uncertainties. This quest for understanding culminated in the discovery of the Higgs boson in 2012, a particle predicted decades earlier but only recently observed, a testament to humanity's relentless curiosity and determination. Trinity also raised profound philosophical questions. At its most fundamental level, what is reality? The principles of quantum mechanics suggest that particles exist in states of probability until observed, challenging our classical notions of objectivity and permanence. Is the universe we perceive a reflection of deeper, hidden truths? Or is it an emergent phenomenon, shaped by forces and dimensions beyond our comprehension? The legacy of the Trinity test is both inspiring and sobering. It marked the moment when humanity wielded the power to alter the fabric of reality, for better or worse. The knowledge it brought has driven advancements in energy, medicine, and material science, while also highlighting the ethical responsibilities that come with such power. The journey to understand the universe continues. From the splitting of the atom to the discovery of the Higgs boson, each breakthrough brings us closer to answering the age-old question, what is everything made of? And, perhaps more profoundly, what does it mean to truly understand the cosmos? As we continue to explore, we must remember the lessons of Trinity. The pursuit of knowledge is a double-edged sword, capable of both great good and unimaginable harm. It is up to us to wield it wisely, ensuring that the legacy of our discovery serves not just science, but humanity as a whole. Splitting the atom, a journey through science and philosophy. The origins of these inquiries date back to the ancient Indian philosophers of the 8th century BCE. They proposed a radical idea: nothing we perceive is truly real. Their extreme reductionist philosophy dismantled the world into its fundamental components. A cart, for instance, could be reduced to wheels, axles, and a yoke. Each of these, in turn, could be further dissected into smaller parts, until nothing remained but tiny, indistinguishable specks. What, then, are the objects of our experience? Are they merely assemblages of these specks, arranged to give the illusion of substance? This existential puzzle resurfaced centuries later among ancient Greek philosophers. Democritus and Leucippus, reflecting on the same problem, concluded that everything could be broken down repeatedly until an ultimate, indivisible unit was reached. They named these fundamental units atomos, meaning uncuttable. This profound concept laid the groundwork for a scientific journey that would span over 2 millennia. The transition from philosophical speculation to scientific inquiry began in earnest in the 19th century. John Dalton, an English chemist, synthesized ancient philosophies with contemporary scientific observations to formulate a groundbreaking theory. Dalton's work revolved around the analysis of chemical compounds. Each compound, he observed, behaved in unique and predictable ways. Methane, for example, consisted of carbon and hydrogen atoms, while nitrous oxide contained nitrogen and oxygen atoms. Dalton postulated that these compounds were constructed from indivisible building blocks, or atoms, specific to each element. Dalton's theory introduced the scientific concept of the atom, aligning with the ancient notion of atomos. Yet, as the 19th century unfolded, evidence began to challenge the idea of indivisibility. Atoms, it seemed, harbored secrets far more complex than Dalton or the ancients could have imagined. By the late 1800s, experiments probing the nature of electric charge unveiled a new kind of particle. J. Thomson, an English physicist, identified the electron in 1897, a negatively charged particle capable of moving independently of atoms. This discovery raised profound questions. If electrons were part of atomic matter, how could atoms remain indivisible? Ernest Rutherford provided a critical piece of the puzzle. In his famous gold foil experiment, Rutherford bombarded a thin sheet of gold with radioactive particles. To his astonishment, some particles rebounded, while others passed straight through. This led him to propose a revolutionary atomic model. Atoms consist of a dense, positively charged nucleus surrounded by orbiting electrons. Rutherford identified protons within the nucleus as carriers of positive charge, establishing the atom as a composite structure. While Rutherford's model explained much, it left one glaring inconsistency: the mass of certain atoms exceeded the combined mass of their protons and electrons. James Chadwick resolved this mystery in 1932 by discovering the neutron, a neutral particle residing within the nucleus. Chadwick's work earned him a Nobel Prize and deepened our understanding of atomic structure. With protons, neutrons, and electrons identified, the atom's indivisibility had been decisively disproven. The discovery of the neutron catalyzed a new era in atomic research. Scientists bombarded atomic nuclei with neutrons, altering their composition and occasionally splitting them. In 1938, Austrian physicist Lise Meitner, collaborating with Otto Hahn and Fritz Strassmann, identified this process as nuclear fission. A single neutron could split a uranium atom into smaller nuclei, releasing an immense amount of energy. Meitner's insights were groundbreaking. She named the phenomenon fission, drawing an analogy to cell division in biology. However, her pivotal contributions were overshadowed by sexism and anti-Semitism, leaving Hahn to receive sole recognition in the 1944 Nobel Prize. The practical implications of fission were profound and terrifying. Scientists quickly realized that a chain reaction of atomic splits could unleash unprecedented destructive power. This realization culminated in the development of the atomic bomb, marking a turning point in human history. The detonation over Hiroshima in 1945 underscored the dual-edged nature of scientific discovery, the potential for both immense progress and unparalleled destruction. With the atom split, the quest for fundamental particles intensified. Protons and neutrons, previously thought to be indivisible, were revealed to consist of smaller components called quarks. Electrons belonged to a different category of particles known as leptons. These discoveries expanded our understanding of matter's building blocks, but they also introduced new mysteries. Were quarks and leptons truly fundamental, or would further exploration uncover even smaller particles? The 20th century's advances in particle physics aimed to unify our understanding of matter. The Standard Model emerged as a framework, categorizing particles and describing their interactions. Yet, significant questions remained unanswered. For instance, what accounts for the vast majority of the universe's mass and energy? The discovery of dark matter and dark energy hinted at realms beyond the Standard Model, suggesting that the journey of exploration is far from over. As we probe deeper into the fabric of the cosmos, we find ourselves circling back to the questions posed by ancient philosophers. What is the nature of reality? Are the particles we observe the ultimate constituents of matter, or are they merely steps on an infinite ladder of discovery? Science and philosophy, once distinct domains, converge in their shared pursuit of these profound truths. The splitting of the atom represents both a triumph of human ingenuity and a cautionary tale. It highlights our capacity to unravel nature's deepest secrets and the responsibility that comes with such knowledge. As we stand on the shoulders of giants, from Democritus to Meitner, we are reminded of the boundless potential of human curiosity and the ethical imperative to wield our discoveries wisely. The story of the atom is far from complete. It is a testament to the enduring quest to understand our universe, a journey that continues to inspire, challenge, and transform humanity. Deeper we go, the story of quarks and the particle zoo. What lies beneath the surface of matter? Could there exist something smaller, something more fundamental than the atoms we once believed to be the indivisible building blocks of the universe? And if so, how deep does the rabbit hole go? These questions have driven the scientific imagination for decades, pushing the boundaries of our understanding of the cosmos and ourselves. This story begins not with laboratory experiments or sophisticated machinery, but with words. James Joyce, the renowned Irish writer, sought immortality through his literary creations. Yet, even in his wildest dreams, he could not have foreseen how his work, particularly Finnegan's Wake, would echo beyond the realm of literature and into the world of particle physics. Joyce's novel, famously dense and cryptic, captured the imagination of a young American physicist named Murray Gell-Mann, who would draw inspiration from its lines to name one of the most fundamental constituents of matter, the quark. By the mid-20th century, physicists had already cracked open the atom, revealing its subatomic constituents, protons, neutrons, and electrons. However, advances in technology soon uncovered a bewildering array of other particles, collectively referred to as the particle zoo. This term captured both the excitement and confusion of a field that suddenly seemed overrun with exotic inhabitants. Among these were hadrons, particles with mass, including protons and neutrons, as well as their more exotic cousins like pions and kaons. The proliferation of hadrons presented a puzzle. While each particle had its own unique properties, there were undeniable similarities between them. Why were they distinct yet fundamentally alike? This enigma echoed the earlier challenge of understanding the periodic table of elements, which had eventually been resolved by uncovering the atomic structure of matter. Physicists now sought a similar unifying explanation for the hadrons. In the 1960s, two physicists working independently arrived at a groundbreaking hypothesis. Murray Gell-Mann, based at the California Institute of Technology, and George Zweig, working at CERN in Switzerland, proposed that hadrons were not fundamental after all. Instead, they were composed of even smaller particles. Gell-Mann envisioned 3 subhadronic particles and whimsically named them quarks, borrowing the term from a line in Finnegan's Wake, 3 quarks for muster mark. Meanwhile, Zweig imagined 4 such components, which he called aces, drawing inspiration from the suits in a deck of cards. Both models provided a compelling framework for understanding the particle zoo. However, these ideas were purely theoretical until experimental evidence could confirm the existence of these subhadronic entities. The Stanford Linear Accelerator Center, established in the mid-1960s, became the proving ground for these bold hypotheses. At 3.2 kilometers long, SLAC's linear accelerator was the longest of its kind, capable of accelerating electrons to energies of 50 gigaelectron volts. By colliding these high-energy electrons with protons and neutrons, physicists could study the wreckage and glean insights into the subatomic structure of matter. In 1968, experiments at SLAC provided the breakthrough. The collisions revealed point-like particles within protons, consistent with Gell-Mann's theoretical quarks. These results confirmed that protons, like atoms before them, were not indivisible. Quarks were real, and they represented a new frontier in our understanding of matter. With the existence of quarks established, the next challenge was to determine their properties and varieties. Over the following decades, high-energy experiments and theoretical advancements identified 6 distinct types, or flavors, of quarks: up, down, strange, charm, top, and bottom. Each flavor possesses unique characteristics, including electric charge, mass, spin, and a property intriguingly named color. The term color in this context has nothing to do with visual hues but instead describes the way quarks interact via the strong nuclear force. This force, mediated by particles called gluons, binds quarks together to form hadrons. Quarks combine in triplets to create baryons, such as protons and neutrons, or in pairs to form mesons. These combinations follow strict rules dictated by quantum chromodynamics, QCD, the theory describing the behavior of quarks and gluons. Quarks are the foundation of all baryons and mesons, which in turn make up the nuclei of atoms. Protons, composed of 2 up quarks and 1 down quark, carry a positive charge. Neutrons, consisting of 2 down quarks and 1 up quark, are electrically neutral. Together, they form the nuclei of every element in the periodic table, giving rise to the diversity of matter in the universe. But quarks do not only form stable particles. In high-energy environments, such as those created in particle accelerators or cosmic events, quarks can also combine into exotic particles like lambda, sigma, and 11 baryons, as well as fleeting mesons. These particles often exist for mere fractions of a second, yet their study provides invaluable insights into the behavior of the strong nuclear force and the early moments of the universe. Quarks are not the only fundamental particles in the standard model of particle physics. Leptons represent another category of elementary particles, including the familiar electron as well as the heavier muon and tau particles. Each lepton also has an associated neutrino, a nearly massless and electrically neutral particle. Together, quarks and leptons form the building blocks of all known matter. Their interactions, governed by the fundamental forces of nature, underpin the structure and dynamics of the cosmos. Yet, the Standard Model, despite its success, leaves many questions unanswered. For all its elegance, the Standard Model does not explain everything. Why do particles have mass? The discovery of the Higgs boson in 2012 provided a partial answer, demonstrating how particles acquire mass through interactions with the Higgs field. Yet, the origins of the Higgs field itself remain a mystery. Moreover, the Standard Model cannot account for dark matter and dark energy, which together constitute approximately 95% of the universe's mass-energy content. Nor does it provide a unified framework for reconciling quantum mechanics with general relativity, the theory describing gravity. As we probe deeper into the nature of matter, we find ourselves revisiting the fundamental questions that have inspired humanity for centuries. Are quarks and leptons truly indivisible, or will future experiments uncover even smaller constituents? Is there a single, elegant theory that can unify all the forces of nature, from the strong nuclear force to gravity? The journey into the subatomic realm has already transformed our understanding of the universe. It has revealed a world of extraordinary complexity and beauty, governed by rules that challenge our intuition yet hold the key to understanding the cosmos. And as we stand on the brink of new discoveries, one thing is certain: the deeper we go, the more there is to learn. The mystery of matter, the hunt for the Higgs boson. What gives matter its substance? Why do particles have mass, and how did they acquire it in the first place? Without mass, electrons would not bind to protons, hydrogen atoms would not form, and the universe as we know it would be a lifeless void. These questions are not only fundamental to our understanding of physics, but also vital to comprehending the very fabric of the cosmos. February in Chicago is harsh. The wind, sharp and relentless, barrels through the streets, carrying the icy breath of Lake Michigan and depositing snow in corners of the bustling city. Yet, amidst the frigid air, the atmosphere inside the American Association for the Advancement of Science's 2009 annual meeting was anything but cold. Scientists gathered with anticipation, drawn to a singular lecture room where the hottest topic in particle physics was about to be discussed: the search for the Higgs boson, often dubbed the God particle. This was no ordinary scientific endeavor. It was a race, a contest of monumental stakes, pitting Fermilab's Tevatron in Illinois against CERN's Large Hadron Collider, LHC, straddling the French-Swiss border. The stakes were immense, as the Higgs boson was the missing piece of the Standard Model of particle physics, a framework describing the fundamental forces and particles shaping the universe. The LHC, a marvel of modern engineering, was purpose-built for this quest at a staggering cost of €3 billion. Yet, just a month after its inauguration in 2008, disaster struck. A catastrophic explosion damaged several magnets in the accelerator, necessitating over a year of repairs. This unforeseen setback handed Fermilab a golden opportunity to take the lead. At the 2009 conference, Fermilab's scientists presented their progress, cautiously optimistic yet candid about the challenges they faced. The search for the Higgs boson was like hunting for a needle in a haystack, with the added complication that no one knew exactly what the needle looked like. The Higgs boson wasn't an arbitrary goal, it was the key to resolving one of the most perplexing mysteries in physics, the origin of mass. The Standard Model, developed over the latter half of the 20th century, provided an elegant explanation for the fundamental forces of nature. It described four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces acted through specific particles known as gauge bosons. For instance, photons carried the electromagnetic force, while gluons mediated the strong nuclear force. W and Z bosons were responsible for the weak force, and a hypothesized graviton was theorized to explain gravity. Experiments confirmed the existence of most of these particles, cementing the Standard Model as a robust framework. However, one glaring issue remained: the question of mass. Quarks, the building blocks of protons and neutrons, had varying masses. The top quark, for example, was 75,000 times heavier than the up quark. Yet, the equations governing particle physics suggested that all particles should be massless. This contradiction was not merely a theoretical inconvenience, it had profound implications for the universe's evolution. Without mass, matter would never have coalesced into stars, galaxies, or life itself. The theoretical breakthrough came in 1964, when Peter Higgs and his contemporaries, Robert Brout and François Englert, proposed a radical solution. They suggested that in the early universe, particles emerged without mass. Soon after, a field, now known as the Higgs field, permeated the cosmos. Particles interacting with this field acquired mass, while others, such as photons, remained unaffected. The Higgs boson, a particle associated with this field, was theorized to exist as its physical manifestation. Finding this elusive particle became a central goal for physicists, for its discovery would confirm the mechanism that endowed the universe with mass. However, detecting the Higgs boson posed an enormous challenge. Its ephemeral nature meant it decayed almost instantly after being created in high-energy collisions, leaving behind a trail of particles that had to be meticulously analyzed. To generate the Higgs boson, scientists turned to particle accelerators, machines that collided particles at nearly the speed of light. The Tevatron, Fermilab's pride, was equipped to probe a specific energy range where the Higgs might appear. Meanwhile, the LHC, with its superior energy capacity and 27-kilometer circumference, was designed to search across a broader spectrum. After its repairs, the LHC resumed operations in 2010, marking the beginning of an intense period of experimentation. Protons collided within the massive detectors, generating unimaginable amounts of data. Analyzing this data required extraordinary computational power and collaboration among thousands of scientists worldwide. On July 4, 2012, CERN announced a momentous discovery. Two of the LHC's detectors, ATLAS and CMS, had independently detected a particle consistent with the Higgs boson. The data showed a clear signal at an energy of around 125 gigaelectronvolts, with a statistical confidence level high enough to declare it a discovery. Nearly 5 decades after it was first theorized, the Higgs boson had been found. Peter Higgs and François Englert received the Nobel Prize in Physics in 2013 for their contributions to this groundbreaking theory. The discovery not only completed the Standard Model but also marked a triumph of human ingenuity and perseverance. The Higgs boson now takes its place alongside the 60 other fundamental particles described by the Standard Model. These include the 6 flavors of quarks, 6 leptons, including the electron and neutrinos, and various gauge bosons. Together, They form the building blocks of matter and govern the interactions that shape the universe. However, the Standard Model, despite its success, is not the final word on the nature of reality. It cannot explain dark matter and dark energy, which make up 95% of the universe's mass energy content. Nor does it reconcile quantum mechanics with general relativity. Moreover, the graviton, the hypothetical particle of gravity, remains elusive. The discovery of the Higgs boson is not the end of the story but a new beginning. Scientists now seek to answer questions that the Standard Model cannot. What is the true nature of dark matter? Are there undiscovered particles or forces that extend beyond the current framework? And can we achieve a unified theory that connects all the forces of nature? To explore these mysteries, physicists are pushing the boundaries of technology and imagination. Plans are underway for more powerful accelerators, such as the proposed Future Circular Collider, which would dwarf the LHC in size and energy capacity. Meanwhile, experiments in astrophysics and cosmology aim to shed light on dark matter and the origins of the universe. The discovery of the Higgs boson is a testament to the power of human curiosity and collaboration. It demonstrates how theoretical ideas, born of abstract mathematics, can lead to tangible discoveries that reshape our understanding of the cosmos. The Higgs field, an invisible yet omnipresent entity, serves as a reminder that even the most fundamental aspects of reality are often hidden from view, awaiting discovery by those bold enough to seek them. As we continue to probe the mysteries of matter, we stand on the threshold of a new era in physics. The journey from the subatomic to the cosmic is far from over, and the quest to understand the universe's deepest secrets promises to inspire generations to come. The Dawn of Matter, a journey into the fabric of the universe. What is the true nature of reality? Is matter, as we perceive it, an immutable building block of the cosmos? Or does it conceal a deeper, more enigmatic truth? From the grandest galaxies to the tiniest particles, the universe challenges us to peel back layer after layer, revealing a complexity that defies comprehension. And yet, as we delve deeper, we find ourselves confronting not just the mystery of matter but the very nature of existence itself. Physicists, armed with precise calculations, estimate the number of fundamental particles in the observable universe. The number is staggering, more than 3 vigintillion quarks and electrons, a 3 followed by 80 zeros. These particles constitute the protons and neutrons in hydrogen and helium atoms, as well as their associated electrons. Even with such a mind-boggling count, when spread across the vastness of space, they average to just 1 quark-sized particle per cubic meter. The universe, it seems, is not so much full of matter as it is dominated by emptiness. Yet, for all the particles we can count and measure, they make up only a small fraction of the cosmos. Matter as we know it, the stuff of stars, planets, and living beings, constitutes a mere 5% of the universe. The remaining 95% is an enigma. 25% is thought to be dark matter, a mysterious substance that holds galaxies together, while 70% is attributed to dark energy, the force driving the accelerating expansion of the universe. Though these phenomena remain poorly understood, the matter we can observe tells a story that stretches back to the very dawn of time. Rewinding the cosmic clock to the very beginning, we arrive at a moment of unimaginable density and temperature. A trillionth of a second after the Big Bang, the universe was governed by a single, unified force. The distinct forces we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were melded into one. Particles, as we understand them, did not yet exist. Instead, there was perhaps a single type of boson, a progenitor of all the particles to come. As the universe expanded and cooled, this symmetry broke. The unified force split into the strong, weak, and electromagnetic forces. Gluons, photons, and W and Z bosons emerged as the carriers of these forces. Yet, at this stage, these particles were massless, and their behaviors were indistinct. It was only after a relative eternity, a trillionth of a second, that the cosmos cooled sufficiently for the Higgs field to emerge. The Higgs field permeated space, endowing certain particles with mass as they interacted with it. Quarks, leptons, and bosons acquired distinct properties, setting the stage for the formation of the universe as we know it. However, the temperature was still too high for quarks to combine into protons and neutrons. Instead, they existed in a turbulent, high-energy state known as a quark-gluon plasma, a primordial cosmic soup. Over time, as the universe continued to expand and cool, quarks began to bind together, forming composite particles like protons and neutrons. These nucleons clustered to form atomic nuclei, which eventually captured electrons to create neutral atoms. Hydrogen and helium emerged as the first elements, and from these building blocks, the universe began its transformation into a complex tapestry of stars, galaxies, and planets. While this story of cosmic evolution paints a picture of ever smaller building blocks nestled within one another, quantum mechanics reveals a more unsettling truth. At the smallest scales, particles such as quarks, leptons, and bosons defy classical understanding. They exist simultaneously as particles and waves, described not by precise locations but by probability distributions. This quantum uncertainty means that particles cannot be pinned down in space and time, challenging the very concept of their existence. Quantum field theory provides an even deeper insight. According to this framework, particles are not standalone entities but rather excitations in underlying fields. The universe is crisscrossed by at least 24 distinct quantum fields, each corresponding to a fundamental force or particle. These fields interact, creating interference patterns that give rise to the semi-stable particles we observe. A proton, for example, is not a solid object but a dynamic interplay of quark and gluon fields, shaped by the strong nuclear force. This perspective transforms our understanding of matter. The tangible objects we perceive are merely manifestations of underlying fields. The Higgs field, electromagnetic field, and others weave an intricate web through space and time, their ripples and interactions giving rise to the illusion of solidity. In this view, the universe is not composed of discrete particles but of continuous, interacting fields, with matter emerging as a transient, localized phenomenon. Even as we unravel the story of matter, vast mysteries persist. Dark matter and dark energy, which dominate the cosmos, remain beyond the grasp of our current theories. The standard model of particle physics, though remarkably successful, cannot account for these phenomena. Nor does it explain the nature of gravity at the quantum level, leaving room for new frameworks that may unify our understanding of the universe. Indian philosophers, nearly 3,000 years ago, speculated that the material world was an illusion. Modern physics, in its exploration of quantum fields and probabilities, echoes this ancient intuition. The universe, at its most fundamental level, may be less a collection of particles and more a symphony of interacting waves and fields, their transient peaks shaping the reality we experience. As we continue to probe the nature of matter, we are reminded that every discovery opens new questions. The journey into the fabric of the universe is far from over, and the mysteries that remain promise to inspire and challenge humanity for generations to come. The Constants of Nature, a journey into the foundations of reality. Beneath the beauty and complexity of the cosmos lies a profound enigma, the constants of nature. These numbers, woven into the fabric of reality, dictate the behavior of everything from subatomic particles to galaxy clusters. Yet, their origins remain one of the deepest mysteries of physics. In the 1940s, physicist Richard Feynman grappled with one such mystery. His groundbreaking work in quantum electrodynamics, QED, explained how electrons interact with light, earning him a Nobel Prize. But one number haunted him, the fine structure constant. All good theoretical physicists put this number up on their wall and worry about it, Feynman remarked. Immediately you would like to know where this number comes from. Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. The fine structure constant, approximately equal to 1/137, measures the strength of electromagnetic interactions. Without it, QED, and much of modern physics, would collapse. Yet, its precise value cannot be derived from theory, it must be measured experimentally. Decades later, physicists still ponder the same question that vexed Feynman: why 1 of 137? The fine structure constant is just one of many constants that underpin our understanding of the universe. These numbers dictate the laws of physics, from the speed of light to Planck's constant, which governs the quantum realm. Others, such as quark mixing angles and Yukawa couplings, reside in the intricate mathematics of advanced particle physics. Without these constants, our theories would be meaningless, unable to describe the interactions that shape reality. Constants like these are more than mathematical curiosities. They hold the keys to understanding the universe's very existence. From the forces that bind particles to the behavior of gravity, these values determine not only how the universe functions but also why it appears as it does. To appreciate the significance of these constants, let us take a journey inward, peeling back the layers of our existence. Begin with a human being, a complex assembly of organs and systems working in harmony. Delve deeper, and you find that these organs are made of cells, each a microscopic marvel of interacting proteins, lipids, and nucleic acids. Zoom further in, and molecules dissolve into atoms, the building blocks of matter. Atoms, in turn, reveal an even simpler structure. Protons and neutrons, nestled in the atomic nucleus, are orbited by electrons. Yet even here, the simplicity is deceptive. Protons and neutrons are composed of smaller particles, quarks, held together by the strong nuclear force. At this fundamental level, we find a universe built from a handful of components, quarks and electrons, bound together by the fundamental forces. These forces, strong, electromagnetic, weak, and gravitational, are the glue of existence. The strong force binds quarks into protons and neutrons and holds atomic nuclei together. Electromagnetism tethers electrons to nuclei, forming atoms. Gravity, though weak on the atomic scale, gathers matter into planets and stars. The weak force governs radioactive decay and nuclear reactions, playing a crucial role in the evolution of stars. Each force depends on constants of nature. The strength of the strong force, the gravitational constant, and the fine structure constant all determine how these forces interact. Without them, the universe as we know it could not exist. But why do these constants have their particular values? Could they have been different? This question leads to one of the most profound puzzles in physics, the apparent fine-tuning of the universe. The constants of nature seem precisely calibrated to allow for the existence of life. Change them slightly, and the universe could become a barren wasteland. For example, if the strong force were slightly weaker, atomic nuclei would not hold together, and no elements beyond hydrogen would form. If the electromagnetic force were stronger, stars would burn out too quickly to support life. Such fine-tuning raises tantalizing questions. Was the universe designed to be this way? Or do we inhabit one of many universes, each with its own set of constants, with ours merely one where life is possible? These are questions that science has yet to answer, but they force us to confront the delicate balance that makes existence possible. To understand the origins of these constants, we must journey back to the beginning of time, the Big Bang. In the universe's earliest moments, temperatures and densities were unimaginably high, and the laws of physics as we know them began to take shape. As the universe expanded and cooled, particles and forces emerged, and the constants of nature crystallized into their present values. But why these values? The standard model of particle physics, though incredibly successful, offers no explanation for the origins of these constants. They are inputs to the theory, not outputs. Some physicists speculate that a deeper theory, perhaps string theory or a multiverse framework, might explain them. Others believe that understanding the constants will require insights that transcend current scientific paradigms. Science thrives on what-if questions. What if the fine structure constant were slightly different? What if the speed of light were faster or slower? Exploring these hypothetical scenarios reveals how profoundly the constants of nature shape our universe. In many cases, even minor changes would render the universe inhospitable to life. This sensitivity underscores the importance of these numbers and deepens the mystery of their origins. The constants of nature sit at the intersection of physics and philosophy. They are both deeply practical, allowing us to calculate and predict the behavior of the universe, and profoundly mysterious, hinting at questions about existence itself. Why does the universe have these particular constants? Are they fixed, or could they vary across time and space? And, perhaps most intriguingly, do they offer clues about why the universe exists at all? Feynman's wonder at the fine structure constant encapsulates the awe and curiosity that drive scientific inquiry. These constants remind us that even in an age of technological and theoretical advances, some mysteries remain as tantalizing as ever. They challenge us to look beyond the equations, to seek the deeper truths that govern reality, and to continue the eternal quest to understand not just how we are here, but why. Are you special? The anthropocentric puzzle in a vast universe. What if the universe were different? What if the stars burned dimmer, gravity pulled weaker, or the forces governing atomic interactions were slightly altered? Would the galaxies still spin? Would planets like Earth form? Would we, sentient beings capable of pondering these questions, exist at all? The answers to these questions lie at the intersection of physics, cosmology, and philosophy, weaving a narrative about our place in the cosmos that is as humbling as it is profound. From the vantage point of Earth, it is tempting to believe that the universe was crafted with us in mind. Early civilizations certainly thought so. To the Babylonians, our world was a flat, circular disk surrounded by the chaos of infinite waters. The Greeks and Romans saw the stars as a celestial stage for gods and monsters, while ancient Chinese cosmology imagined the heavens as concentric shells revolving around Earth. Science, however, has steadily dismantled this comforting illusion. In 1543, Nicholas Copernicus shattered the geocentric worldview, placing the Sun at the center of our planetary system. This dethroning of Earth continued into the 20th century as Edwin Hubble's telescopes revealed that our Sun is but one of billions of stars in the Milky Way, which itself is just one of potentially trillions of galaxies in the observable universe. Today, the cosmos appears boundless, vast, and largely indifferent to our existence. This growing sense of insignificance is formalized in the Copernican principle, a cornerstone of modern cosmology. It asserts that Earth occupies no special place in the universe. The laws of physics are uniform across space and time. From any vantage point, the universe looks essentially the same. Humanity, in this view, is not central but peripheral, a mere bystander in a vast cosmic drama. While the Copernican principle encourages humility, it does not fully explain why we observe the universe as we do. In the 1960s, Princeton astrophysicist Robert Dicke introduced a temporal dimension to this question. Dicke argued that intelligent observers like us could only exist at specific epochs in the universe's history, a conclusion rooted in the physics of stellar evolution. In the universe's infancy, heavy elements such as carbon and oxygen did not exist. These elements, essential for life, were forged deep within the cores of the first stars and scattered across space when those stars died. It took billions of years for subsequent generations of stars to enrich the cosmos with the building blocks of complexity. Conversely, in the distant future, the universe will grow increasingly inhospitable as stars like our Sun exhaust their fuel and fade into white dwarfs, leaving only dim red dwarfs to light the cosmos. Life as we know it can only emerge during a relatively narrow window, a golden age of habitability, which we currently inhabit. In 1973, Australian physicist Brandon Carter expanded on this idea at a conference marking Copernicus's 500th birthday. Carter proposed the anthropic principle, a counterpoint to the Copernican principle. While our location in space may be unremarkable, he argued, our existence imposes constraints on the conditions we observe in the universe. For intelligent life to arise, the cosmos must meet certain prerequisites, and these prerequisites are anything but ordinary. At the heart of the anthropic principle lies a delicate balance. The universe's fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, determine everything from the behavior of stars to the chemistry of life. These forces are governed by constants of nature, unchanging numbers that dictate their strength and interactions. Slight variations in these constants would lead to a radically different universe. For example, if gravity were slightly stronger, stars would burn through their fuel too quickly, leaving insufficient time for complex life to evolve. If it were weaker, stars might never ignite, and planets like Earth would not form. Similarly, if the electromagnetic force were altered, atoms would not bind together properly, rendering chemistry and life impossible. The strong nuclear force, responsible for binding protons and neutrons in atomic nuclei, must also be finely tuned. A slight increase in its strength would prevent the formation of hydrogen, the most abundant element in the universe, while a slight decrease would destabilize all nuclei. This fine-tuning extends to the elements themselves. The iron in Earth's core, the silicon in its crust, the oxygen in water, and the carbon in living organisms all owe their existence to the precise conditions within stars. Gravity compresses stellar cores to immense densities and temperatures, enabling nuclear fusion. Through fusion, lighter elements like hydrogen and helium are transformed into heavier elements. Over billions of years, the cycle of stellar birth, death, and rebirth has enriched the universe, creating the raw materials for planets and life. The anthropic principle raises profound questions. Are the constants of nature the way they are by design, or are they the product of chance? Some physicists suggest that our universe is just one of many in a multiverse, each with its own set of physical laws. In this scenario, we inhabit a universe where the conditions happen to be right for life because, by definition, only such a universe could produce observers to ponder its nature. Others see fine-tuning as evidence of a deeper, underlying principle or even a designer. The anthropic principle does not resolve these debates but instead highlights the extraordinary set of circumstances that make life possible. It challenges us to think about the universe not just as a backdrop for existence but as a participant in the story of life. The questions do not end here. What if gravity were slightly stronger, electromagnetism slightly weaker, or the laws of physics entirely different? Would stars still shine, or would the universe be a dark, lifeless expanse? Exploring these what-if scenarios helps physicists understand the robustness of the universe's design and the constraints that govern its evolution. As we ponder these questions, one thing becomes clear. While we may not occupy the center of the universe, our existence is deeply tied to its fundamental properties. The forces and constants that shape the cosmos also shape us, linking the vast and the minute in a delicate, interdependent web. The magic numbers, constants of nature and the universe's blueprint. Would stars still ignite? Would atoms form? Would life, as we know it, even exist? These questions probe the very heart of physics, revealing how the universe's magic numbers shape everything we observe and experience. At the dawn of the 20th century, physics faced a conundrum. Scientists could not explain why objects glowed the way they did when heated, shifting in color from red to white. Max Planck, one of the era's most brilliant minds, sought a solution. He experimented with classical ideas, only to find them inadequate. Desperate, Planck introduced a radical concept: energy is quantized, emitted and absorbed in discrete packets he called quanta. Planck's innovation was born not from clarity but from necessity. What he considered a mathematical trick turned out to be the foundation of quantum mechanics, a paradigm shift that redefined physics. Embedded within his equations was a number, Planck's constant, that became central to understanding the quantum realm. This constant explained phenomena as varied as the glow of hot objects, atomic structures, and the interaction of light and matter. Today, Planck's constant is a cornerstone of quantum physics, a reminder that even the most desperate ideas can illuminate new paths. Physics is written in the language of mathematics, a precise tool for describing and predicting the universe's behavior. Newton's laws of motion tell us how objects move, while Maxwell's equations describe the interplay of electricity and magnetism. Yet, these equations require something more, the values of the constants of nature. Without these constants, the equations are mere abstractions, unable to connect theory with reality. For example, Newton's law of gravitation depends on the gravitational constant, which measures the strength of gravity. Maxwell's equations rely on the permittivity and permeability of free space to define the propagation of electromagnetic waves. These constants are not derived from theory, they are measured, extracted from the natural world through meticulous experiments. In 1798, Henry Cavendish conducted one of the most delicate experiments in scientific history. Using a torsion balance housed in a wooden box to shield it from disturbances, Cavendish measured the gravitational attraction between lead spheres. His work revealed the density of the Earth and provided a means to calculate the gravitational constant. Cavendish's weighing of the world was an extraordinary achievement, with his results remaining unmatched in precision for a century. Today, the quest for precision continues. Constants like the speed of light and Planck's constant are known to astonishing accuracy, often to many decimal places. These values anchor the equations of physics, making them indispensable tools for exploring the universe. Beyond gravity and light, other constants define the universe's behavior. The strength of the Higgs field determines the masses of fundamental particles. Quark mixing angles govern how quarks transform into one another, influencing the behavior of matter at the subatomic level. These constants are cataloged in physics textbooks, serving as the foundation for scientific inquiry. Dimensionless constants, which lack units, are particularly significant. For instance, the fine structure constant, approximately equal to 1/137, measures the strength of electromagnetic interactions. Another example is the ratio of the proton's mass to the electron's mass, roughly 1836. These numbers are universal, unaffected by the units we choose to describe them. Yet their origins remain a mystery. Why 1/137? Why 1836? What if these numbers had been different? To understand the importance of these constants, physicists simulate hypothetical universes with altered values. What if gravity were 1,000 times stronger? Planets would orbit their stars more rapidly, stars would burn through their fuel faster, and the cosmos would evolve at a breakneck pace. What if electromagnetism were weaker? Atoms might fail to form stable bonds, rendering chemistry and life impossible. Such thought experiments reveal the fragility of our universe's design. Small changes to the constants of nature could render the cosmos unrecognizable. The fine-tuning evident in these constants suggests a profound connection between the laws of physics and the emergence of complexity. To truly grasp the impact of the constants, we must journey back to the universe's beginning. In the moments after the Big Bang, temperatures and densities were extreme. Fundamental forces began to emerge, their strengths encoded in the constants we observe today. These forces shaped the cosmos's evolution, guiding the formation of atoms, molecules, stars, and galaxies. Gravity, electromagnetism, and the nuclear forces worked in harmony to create the elements necessary for life. Stars fused hydrogen and helium into heavier elements, scattering them across space when they exploded as supernovae. These elements coalesced into planets, setting the stage for the emergence of life. Altering the constants would disrupt this delicate balance, potentially preventing the universe from ever reaching such complexity. The apparent fine-tuning of the constants raises profound questions. Why do they have the values they do? Some physicists suggest that our universe is one of many in a vast multiverse, each with its own set of constants. In this view, We exist in a universe where the conditions happen to allow for life, simply because only such a universe could produce observers to ponder its nature. Others propose that deeper principles, as yet undiscovered, dictate the values of these constants. String theory and other frameworks offer tantalizing hints, but the ultimate answers remain elusive. The fine-tuning of the constants invites both scientific and philosophical reflection, challenging us to explore the intersection of necessity, chance, and design. The constants of nature are the universe's magic numbers, governing everything from the motion of planets to the behavior of subatomic particles. They are the scaffolding on which the cosmos is built, their precise values enabling the emergence of complexity in life. Changing the rules of nature, a journey through hypothetical universes. As we peer into this multiverse of possibilities, we begin to grasp how uniquely fine-tuned our universe truly is, and why life, as we know it, might be an exceedingly rare phenomenon. Modern astronomy has achieved remarkable success in explaining the universe by adhering to the rules of physics. Around the globe, scientists use supercomputers to construct synthetic universes, translating the equations of cosmology and astrophysics into intricate computational models. These simulated universes, spanning billions of light years and billions of years, provide a window into cosmic evolution. Projects like the illustrious TNG trace the interplay of matter and radiation within expanding, synthetic universes. These virtual realities reveal the dance between cosmic expansion, which pulls matter apart, and gravity, which draws it together. In these simulations, matter clumps into proto-galaxies, gas flows into stars, and the life cycles of stars play out. Some stars end their lives in brilliant supernovae, scattering heavy elements into space, while others quietly fade into white dwarfs. The simulations track how these elements, the building blocks of complexity, are formed and dispersed. Inspection of these synthetic universes reveals familiar structures, galaxies, star clusters, and clouds of gas. Some are pristine remnants of the Big Bang, while others are enriched with heavier elements forged in stellar cores. The striking resemblance between these synthetic universes and our own confirms that the laws of physics govern the cosmos's evolution, from the largest galaxy clusters to the smallest atomic interactions. If we can construct synthetic universes based on our own physics, why not imagine universes governed by different rules? The process seems deceptively simple: tweak the constants of nature, adjust the computer code, and observe the results. But is it truly that straightforward? We are the result of a complex web of interactions spanning billions of years. To determine whether life could arise in other universes, we must unravel this web, cutting its threads and forging new connections. Simplified models provide insights, but to capture the full complexity of alternate realities, scientists rely on supercomputers to simulate hypothetical universes. The results are sobering: most possible universes are lifeless and sterile. Calculations reveal a vast ocean of dark, barren universes. In many, there is no structure, no galaxies, stars, or planets. In others, complexity fails to arise. There is no periodic table of elements to support chemistry. Amid this bleak landscape, islands of complexity and potential habitability are vanishingly rare. In our universe, the masses of the fundamental up and down quarks are finely balanced. This balance ensures that the proton is lighter than the neutron, causing neutrons to decay into protons shortly after the Big Bang. This decay filled the cosmos with protons, forming the hydrogen atoms that fuel stars and serve as the foundation for heavier elements. If the down quark were lighter, neutrons would be less massive than protons. The Big Bang would have produced a universe awash with inert neutrons. Stars composed of neutrons might form, but without the nuclear reactions that fuse elements, there would be no periodic table, no complex chemistry, and no life. Conversely, a heavier down quark could destabilize protons, erasing hydrogen and snuffing out the possibility of star formation. Electrons orbit atomic nuclei, enabling the formation of molecules. Their mass, relative to the nuclear force, dictates the stability of these orbits. In our universe, the nuclear force is thousands of times stronger than the electromagnetic force, ensuring stable atoms and diverse chemistry. If electrons were more massive, their high-speed orbits would cause nuclei to wobble. This instability could prevent atoms from bonding, leaving a universe populated only by individual atoms, a gas with no molecules, no solids, and no life. Chemistry, the engine of complexity, hinges on this delicate balance. Gravity plays a pivotal role in shaping the universe. It draws matter together to form galaxies, stars, and planets. But its strength must be just right. If gravity were weaker, the expanding universe would remain a diffuse soup of hydrogen, never coalescing into stars or galaxies. If gravity were stronger, matter would collapse into black holes before stars could ignite. Even within this narrow range, gravity dictates the lifetimes of stars. Too weak, and stars fail to sustain nuclear reactions, remaining as inert balls of gas. Too strong, and stars burn through their fuel too quickly, leaving no time for the evolution of life. In our universe, dark energy drives the accelerating expansion of space. During the universe's early epochs, matter dominated, allowing gravity to draw material into stars and galaxies. Approximately 5 billion years ago, dark energy overtook matter as the dominant force, accelerating the universe's expansion. If dark energy were stronger, this acceleration would have begun earlier, preventing matter from collapsing into stars. Hydrogen atoms would drift alone in cold, empty space. Conversely, a universe without dark energy might eventually collapse under gravity's pull, snuffing out the possibility of long-term complexity. The balance between dark energy and matter determines the universe's fate and its potential for life. Beyond gravity, dark energy, and particle masses, other constants influence habitability. The speed of light, the scale of quantum mechanics, and the stability of dark matter all play roles in shaping the cosmos. For some constants, small changes yield negligible effects. For others, even a slight adjustment would render the universe unrecognizable and uninhabitable. Among the multiverse's countless possibilities, our universe stands out as a rare exception. It is an island of complexity in a sea of sterility, its constants perfectly balanced to support life. This realization answers one question: how are we here? We exist because of an almost impossibly precise interplay of physical laws, honed over 13.8 billion years. But this answer raises a deeper, more profound question: why? Why does our universe have the rules it does? Are these constants the result of chance, necessity, or something beyond our comprehension? As we continue to explore the multiverse and the fundamental laws of nature, we inch closer to understanding not only how we exist, but why the universe is the way it is. Why are we here? Exploring the enigma of existence. The constants of nature have long fascinated physicists, their seemingly arbitrary values shaping the cosmos in profound ways. From the speed of light to the gravitational constant, these numbers dictate the behavior of the universe at every scale. For some, their precise values seem to demand explanation, hinting at a deeper truth hidden within the fabric of reality. Take, for example, the fine structure constant. This dimensionless number, approximately equal to 1/137, measures the strength of electromagnetic interactions. Sir Arthur Eddington, the first to experimentally confirm Einstein's general theory of relativity, was captivated by this number. He speculated that it might be exactly 1/137, even connecting it to the total number of protons in the observable universe. But as experimental measurements became more precise, Eddington's hypothesis fell apart. The fine structure constant is not tied to any simple integer, and its true nature remains a mystery. As science advances, the web of constants needed to describe the universe grows smaller. Before James Clerk Maxwell, electricity and magnetism were described by separate constants. Maxwell's equations unified these forces, introducing a single constant, the speed of light. Such unifications hint at the possibility of an ultimate theory, a theory of everything that might dispense with constants altogether, reducing physics to pure mathematics. But would such a theory truly answer the question of why we are here? Or would it simply shift the question to a higher level? Even if the laws of physics could be expressed as mathematical relationships without constants, we would still be left asking why these relationships permit the existence of a universe capable of hosting life. This brings us to the concept of fine-tuning. The constants of nature are not just arbitrary numbers, they appear delicately balanced to allow for complexity, structure, and life. A slight alteration in the gravitational constant, for instance, could prevent stars from forming, while a change in the fine structure constant might disrupt the chemistry necessary for life. Such precision has led some to propose that the universe was designed with purpose, perhaps by a divine being or fine-tuner. The fine-tuning argument aligns with many religious worldviews, suggesting that the universe's life-permitting properties are evidence of intentional creation. Yet, alternative explanations challenge this perspective, offering visions of existence that are no less profound. One such alternative is the simulation hypothesis, championed by Oxford philosopher Nick Bostrom. According to this idea, our universe could be a sophisticated simulation run by a higher intelligence. As computers become more powerful, humans may one day simulate entire universes, complete with conscious beings who perceive their reality as genuine. If such simulations are possible, it follows that our own universe might be a simulation created by an advanced civilization. The laws of physics would then be nothing more than computer code, optimized to produce an interesting universe. In this framework, we find ourselves in a universe with life and complexity because a simulated cosmos devoid of these features would be unworthy of computational resources. While the simulation hypothesis is philosophically intriguing, it poses challenges for empirical science. How can we test whether we are living in a simulation? If our reality is governed by computer code, then any attempt to investigate the base reality might be inherently limited. And even if we accept the hypothesis, it raises further questions. Is the universe simulating us also a simulation? Are there turtles all the way up? Another explanation for fine-tuning lies in the concept of the multiverse. Rather than being unique, our universe could be one of countless others, each with its own set of physical laws. In this scenario, the constants of nature vary across universes, their values determined by a random process. Most universes would be sterile, lacking the conditions necessary for life. Ours, however, is one of the rare exceptions, its constants coincidentally aligned to permit complexity. The multiverse hypothesis shifts the question from why are the constants fine-tuned to why do we observe this universe? The answer is anthropic. We exist because we inhabit a universe that allows for observers. If the multiverse is real, then our existence is not special but inevitable within the subset of universes that support life. Despite its appeal, the multiverse hypothesis faces significant criticism. Some argue that it is wasteful, positing an infinite array of lifeless universes to explain one that harbors life. Others contend that it is unscientific, as the existence of other universes may be fundamentally untestable. Without observational evidence or predictive power, the multiverse remains more a philosophical concept than a scientific theory. Whether through divine intervention, computational simulation, or the multiverse, the question of why we are here continues to elude definitive answers. Each explanation offers insights but also raises further questions. Why would a creator fine-tune the universe? Why would a simulation prioritize complexity? Why does the multiverse generate universes at all? These questions remind us that our understanding of existence is still in its infancy. As we probe deeper into the cosmos and refine our theories, we may uncover new principles that shed light on the mystery of our origins. For now, the search for answers is as much about the journey as the destination, inspiring us to explore, imagine, and question. Why are we here? This question transcends science, touching on philosophy, theology, and the human condition. It challenges us to consider our place in the universe, not just as passive observers but as active participants in the unfolding story of existence. As we grapple with this enigma, we are reminded of the vastness of the cosmos and the improbability of life. Whether we are the product of divine design, computational artistry, or cosmic chance, our existence is a testament to the complexity and wonder of the universe. And in seeking to understand it, we honor the very curiosity that makes us human.